if we have a matrix in a block diagonal form like this, in a sense it's telling us, right, that we're operating on invariant subspaces. So we can take our vector space and slice it up into spaces that, when they're operated on by a matrix like this, they just map back into that same subspace. Right? So if we can cook up some invariant subspaces, then we could write down a matrix like this in principle. One's obvious, right? It's the totally symmetric representation. It'd be a totally symmetric function, right? So if I have an arbitrary function rho, and I take that function and I write it out this way. So this 6 here is just for normalization. You can see it's invariant under all operations of the group. So that's easy to see, right? Because although I'm running out of space, we define the group action. So if we have some element of the group G, we define the action of that group UG on this function just to be. So in this case, right, we just bring it in underneath the argument. So if I operate here with some operation of the group and I bring it in here, then I just change all these x's. But in the end, it's just going to end up permutating around all these arguments to the thing, but I get back the same function. D is just the way of, so this operator operates on the function space, right? So this could be whatever you need it to be. And then this operates on the underlying space, right? So just D is just the way of saying it's another representation of the group. But the idea is that when the group element operates on a function, you just bring it underneath the argument sign. This is its space all in itself. If I operate with any member of the group, I just get the function back. And since that would be, I guess maybe I can use that. That'd be like here. I could write a 1 here, right? Because if I use this as a basis function, operating on it with this matrix, it's just going to take it back to itself. So I can write down a 1 in that space. And it's one dimensional, right? So I just have this 1, 1. So in the end, we want to get something that is 6 by 6, because this is 6 by 6. Another thing I can write down, I'll call it, I guess, rho 2, is something that's anti-symmetric. If I operate on it with certain group operations, it's going to give me back the same function. And with the other ones, it's going to give me back the same function, but with a minus sign. So I can construct, I guess a good way to motivate it is that the parity of permutation operators like this, right, is like -1. So you might think, just guess, let me put -1 in front of those. The parity of rotation operators is +1, so I'll just leave the pluses in front of those. Right, so I'm just going to write that down, and we can stare at it for a minute and see. So the parity of this one is +1, then here. For instance, I'll just do this quickly without working it out, but let's say I operate here with one of the permutation operators. Then I'm going to bring it in here, so I'll get a permutation here. I'll get permutations on each one of these, except one of them is going to turn into the identity, right? But it'll have a minus sign now in front of it.
So let's say it's sigma 1, 2.
Yeah, well, let's just do it. How about that? Sigma 1, 2 on what I've called rho 2x. Right, so I get 1/6. I get rho of sigma 1, 2x minus rho. So sigma 1, 2 on sigma 1, 2 is the identity because it's the inverse of itself. So I get x here. Sigma 2, 3. Does anybody know off the top of their head what 1, 2 and 2, 3 is? If not, I can just work it out. Yeah. I guess it doesn't matter, right?
Yeah.
This one's going to give me the identity. These two are going to give me the other two, whatever they are, right? So that's a good point. So this would be rho, let's just say sigma 2, 3 x minus rho of sigma 3, 1, x. And then, yeah, you're right. I've messed this up. That makes sense. Yeah, I probably should fill this out and it would help. Then let's just fill this out. This is E sigma, I guess it would be what? Sigma 1, 2 on sigma 2, 3 is C 1/3. So, thank you. Then this one must be C 2/3, right? And then I have the two rotations, but those are going to give me two permutations. So then I'll have plus rho C23x plus rho C31x, right? If you stare at that, you can see it's the minus of this, I think, right? Because now these two things have picked up minus signs, and these things have all picked up plus signs. And if you operated on it with one of the rotations, you could probably go through and figure it out. But you can also just see it by thinking about the way that the rotations would change the parity of these things under. But you'll basically get back the function itself without the minus sign. Right. I guess I'm saying for any group element, its matrix representation in the block diagonal form, we know these first two parts are going to be this form. It has to be 6 by 6, so there's a 4 by 4 block left. I guess I'm going to erase this. Is that all right? So if we kind of motivate ourselves off the fact that this rotation group right here, so the identity element with these two elements is a subgroup, we can use something we did last Thursday when we wrote down the generalization of symmetrization and anti-symmetrization of a function. Hopefully everybody remembers this. I'm just going to write these down, but I'm just stating that your motivation maybe for writing those down would be the fact that this is a subgroup of our group G3. So again, the 1/3, I guess you can think is just for normalization. So that gives us two functions, and I think you can see that these two functions are invariant under rotations. Right? So if I put a rotation here and I move it inside here, then I'm going to get one of these is going to turn into the identity, and I'll pick up a rotation on that side, right? Okay, I mean the space is invariant. So if I operate on any one of these functions with a rotation, it's going to bring me back into the space spanned by these two functions. That's what I mean by invariant, I'm sorry. So this forms a subspace that's invariant under rotations. However, if I operate on it with permutations, right, it's going to take me out of the subspace. So I can write down two more functions that will give me a subspace that's invariant under all the operations. Yeah, thank you. I guess I'll write down one here. Right? So I'll call this row 5. Right, and on this one, I guess I can just pick an arbitrary permutation and put it into these arguments, right? So for that one, for instance, I could write down rho sigma 1, 2 of x plus omega. So sigma 1, 2 on C 1/3. Sigma 1, 2, C 1/3 gives me sigma 2, 3. Actually, I went backwards. What I actually should be doing is C 1/3, right? C 1/3 on sigma 1, 2, which I don't have it filled out, but from what I have here, it must be sigma 3, 1. So this should be sigma 3, 1, right? So that gives me 1. So I need one more. And I mean, you could already see that I need one more because we're in a 6-dimensional space. So I need to write down 6 vectors to span it. So the last one. It would be the analog of this, but with all these substituted in. All right. Now, I won't work it out, but hopefully you'll take it. So we could see that this was invariant under, this subspace is invariant under rotations. This subspace is invariant under permutations. Right? Because if I put a yeah, 5 and 6. But all 4 of these taken together is a subspace that's invariant under all operations of the group. So that's what would give us our 4x4 block here. Yeah, exactly. Yeah, so this one I can't just write plus or minus, but for instance, if you were to go work it out for the action of sigma 2, 3, let's say, by just acting on this subspace with sigma 2, 3 and seeing what it maps you into, right, you'd be able to work out that representation would be something like 1 minus 1. Right, we knew these 2 things. And then in this diagonal, you'd have something like. Right, so you'd have a 0 here. Hopefully, the form of that works right, but the point is it splits down into a block like this, right? So then I'd have it in a block diagonal form. And I could do these with all these different vectors. I could just work out what these things are. And you'd find that when you did it, all of them would give you some sort of block diagonal matrix. So my whole point in doing that was just to demonstrate, just I guess sort of by guessing, that you can take the regular representation and indeed reduce it down to something with block diagonal form. So what we can think of each one of these functions as, and the other 2 are erased, right, is that I've taken some arbitrary function and projected it into the basis for the invariant subspaces. Right? I've taken it, and now I can write my function out. Although I've erased the other 2, I think you could see that if you added up the first 4 of them, it would actually just give you your function back, right? So this is just another way of rewriting my function. But now I can see the action of the group on it easily, because it doesn't take it out of the invariant subspaces. So I did this example by sort of guessing, but it turns out there's a more systematic way to do it. And that's the projection operators that we kind of briefly talked about on Thursday. So I'll write down the formulas for those and just talk about them really quick.